Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Hi, I'm Dave Whitehead. I'm the CEO at Schweitzer Engineering Laboratories. And today I'm here with Bryan Fazzari. And Bryan is a electrical engineer at SEL who's designing our distribution automation systems to really control wide area parts of our power systems. And I got interested in distribution automation. It's a big buzzword in the electric industry. And I thought it'd be fun to sit down with Bryan, pick his brain on what's all this excitement about in distribution automation. So with that, Bryan, welcome.
Thank you, Dave. It is exciting. Happy to be here.
Okay, in previous podcasts, I've discussed protection technologies like traveling wave and other things. And the protective relays not only detect faults, but they issue commands to circuit breakers to open them up. 80% of all faults are transitory, so the relay waits a little while and the fault will eventually burn out. The relay will then close back or close the line back in, and lights come back onto your house. And this all happens in a matter of, a handful of seconds or so. And in my mind, that's a pretty automated process. But it seems like there's more to this automation stuff, especially from you automation engineers, than the simple, automated system I just described with the relay. So, Bryan, how do you define automation?
Yeah, that's a good intro. So for most folks, when we talk about a protective relay, especially if you work for Schweitzer, you talk about the difference between the traditional electromechanical relay and a microprocessor-based relay. And what makes that microprocessor-based relay unique is its microprocessor. There's a computer inside it. For me, though, as an automation engineer, it's the communications port. It lets the relay explain itself. So when that 80% of faults occurs, the relay is going to trip and it's going to reclose if it has reclosing capability. In that event, the power is still on, but I can collect an event. I can get an idea for, maybe vegetation slapping against the line. Can I ask it to explain why it tripped in the first place? And for that 20% or so of faults that are classified as permanent, where you end up with an outage, that relay stays open, the goal of automation is to collect data from that device and all the other devices on the system, on that circuit there, and organize it. So there's reams of data available from all these devices. And then what do we do with that information? Can we figure out where that fault is? Can we do something about reducing the outage area? It's the act of taking all this information and making it actionable and useful, whether that's to a human or to an automation type system like a wide area control system that's going to do something on its own.
And really then, what is the objective of these automation systems? If I was trying to explain this to my mom or my grandmother, Edison and Tesla really got the power system industry going 100 years ago, and you know what, the lights stayed on pretty well, and we've probably done incrementally a better job year over year of keeping them on. So really, what is the objective of this, the automation, certainly on the as it relates to the power system?
Okay, so when Edison and every engineer working on the power system at that time started, we knew where power was being generated and we knew where it was being consumed. And that's still true in a lot of places today, but that is changing. So if you think about, especially you and I are both here in the Pacific Northwest, there are a lot of dams, hydroelectric facilities. A lot of our power comes from those dams. And so power is generated there at the river. It's transmitted over a transmission line to a substation where it's stepped down in voltage a little bit, and then it goes into what we call the distribution system, which is a web of lines above and below ground that ultimately deliver power here to my house where I'm sitting, or to SEL in Pullman, a manufacturing facility. Everywhere power is needed, the distribution system transmits it. And we know how power is flowing there, right? It's coming from the dam and it's going to where it's consumed. That's changing. So we're finding ourselves in a place in history where generation's popping up everywhere, whether it's wind, whether it's microgrids, whether it's solar facilities. These aren't just being, distributed throughout the system. They're being connected to the distribution system close to where the load is. And so the flow of power is becoming less certain as far as directionality from day to day, minute to minute. And we're adding devices to the system. So we don't just have breakers inside the substation anymore. Those things are awesome to watch operate. They're about the size of a truck a lot of the time. We've got devices on top of the pole. We probably all drive by them on the way home. These devices are called reclosers, and they're able to break that line between you and the dam into hundreds, maybe thousands of different pieces if there's a problem somewhere. And so each of those devices can give us information and help us draw a clearer picture of the grid and do something automated with that. But it takes some effort to layer intelligence on top of that and figure out how to make sense of all that information and do something in a reasonable amount of time.
So if I were to play back what you just told me, and I was going to relate it to my mom, back with the Tesla or the Edison days, energy was created at a generation facility. Maybe it's a coal plant or a dam, as you pointed out. Then it gets stepped up into the transmission system and then stepped back down to various levels till it finally gets to my house. And it was almost like a one-way power flow. I'm kind of oversimplifying it, but a one-way flow of power from generation all the way to where it gets consumed in a household load or in a factory. And these days, the challenge is these little generating facilities are getting put into the distribution side, if you will. And so it's no longer the power system is a one-way flow. It's all bi-directional. And all of these little generating systems are then competing against each other. And you need to, for optimization of power flows and economies of scale and efficiencies, you need to coordinate all of these little generation systems. And we do that through what I'm assuming is this distribution automation that we keep hearing about in the utility industry.
That's right. So distribution, we've tacked onto the front of the term automation now, right? So now it's its own thing. It's got its own acronym, right? DA. Why does it have its own thing? Well, transmission and distribution, one of their biggest differences, besides the fact that transmission tends to be much higher voltage, is if you were to simplify a transmission line or system into a straight rope, then a distribution system is what that rope looks like after my 3-year-old son Benjamin plays with it for 30 seconds. It's a web, and necessarily so. We live in a distributed economy. We live all over the place, and we all need power. And so these power lines split and split and split and get all eventually end up in our yards, connecting to our main circuit breakers out in the garage. And so there's a lot of conductor out there. There are a lot of places where there can be a fault. And so we have this proliferation of smart devices like microprocessor-based relays, voltage regulators, capacitor bank controls. There's all kinds of stuff out there that makes sure that the power getting to us in our walls is at 120 volts or very close and is at 60 hertz. And all these pieces of equipment need to be monitored and coordinated, and they can all be optimized to be more efficient in their operation. So DA is kind of an overloaded term these days. If you were to Google it, you may come away wondering, okay, now what is DA again? So I'll be specific here. The most common DA solutions, there's 3 of them that I spend a lot of time focusing on. The first is volt-var optimization. The second is distributed energy resource integration. And the last one is called FLISR. And I'll say it as an acronym because it's fun to say, but FLISR stands for fault, location, isolation, and service restoration. So those 3 are the most common.
Well, you convinced me that we just can't keep adding resources onto the distribution system and expect it to all take care of itself. So there does need to be some kind of automation control going on. And you referenced 3 particular applications that would fall under this distribution automation. So let's touch on each one of those. The first one you mentioned was this volt-var optimization. What is volt-var optimization, and why should I care about it?
Okay, so when power is generated and shipped out to our houses, there are 2 components to it. And you'd call it real power and reactive power. And without getting into any math or detail or anything, reactive power is measured in something called VARs. And so that's where this term VAR comes from. Volt-var optimization When a utility is interested in something like that, they're looking at two different objectives. They want to make their distribution system more efficient, and they want to save money. What do I mean by that? So the objective of volt-var optimization is twofold. It's to reduce reactive power flow and to decrease the voltage on the feeder. We'll look at those one at a time here. If you reduce reactive power flow, you reduce the amount of power lost in the line between the substation and our houses. So again, you think about this distribution system as a web with thousands and thousands of miles of conductor. You're going to lose significant power in those conductors. By reducing the reactive power flow, you reduce the losses in those lines. But not only that, a lot of electric utilities don't generate all their own power. They purchase it. And so you have this concept of a purchase power location where they're connected to someone that's generating power and is selling it to them. The amount that they pay for that is often a factor of what we call power factor, which is think of it as the ratio of real to reactive power on their system. So the better they can get their power factor, the more minimized they can make their reactive power flow, the better rate they'll get when they purchase that power. So they can save money that way. Now, what about this voltage reduction thing? We all expect 120 volts in the wall. So why are they reducing voltage on us? So before any of us panics, there is a standard there where they're allowed to reduce the voltage a little bit, not very much, but a little bit. And it ends up for certain types of loads, you can actually save energy that way. And those savings are reaped by you and me, the people behind the meter, the people consuming the power. So why would a utility want to reduce voltage? It ends up what they're looking for is to reduce what we call peak demand, which is when the most power is demanded of a utility. That tends to be between 5 and 6 in the evening. It's when we all come home and start cooking and do our laundry and turn the AC down and all that. So what they're wanting to do is reduce that peak, the highest peak. So you can think of the power grid as like an exotic supercar. It's got a massive amount of power that it can transmit, but it only needs to transmit that much power for a couple hours a day. But once we go to bed, we're not consuming as much power anymore. So they're looking for ways to do what's called peak shaving, reduce the total power that is needed in those last couple hours of the afternoon.
That's interesting. So I've heard quite a bit of volt-var, and there's been some discussion about how to optimize volt-var either with regulators or cap banks to manage both the voltage and the VARs respectively. But I think those assumptions are based on particular types of load, like resistive load for getting some benefit from voltage reduction, and VARs. You want to cancel out the inductive effect of, say, power lines and what have you. But with the loads we have today, especially with inverters and switching power supplies, which are constant power devices, if you lower the voltage, it's just going to suck more current out of the power system to maintain that constant power. And I think at the end of the day, you end up punishing the power system by reducing the voltage. So does volt-var optimization really work?
That's a great trade-off you just highlighted. So if the load, when you reduce voltage, is just going to pull more current through the line, well, then you increase your line losses. So it can be a counterproductive exercise in some cases. So volt-var optimization does work, but it is a difficult problem. These quantities that we're trying to optimize are intertwined with each other. You mess with one, you're messing with all of them. And so you may try to optimize one or two, and you may end up violating some sort of constraint in the others. And so attempting to solve the volt-var problem is a challenge. If you were to look at it from a data science point of view, it ends up being what we call a mixed integer, nonlinear, non-convex problem. What does that mean? It means it's hard for a computer to solve. And a computer is what we use for these types of solutions. So I call it the simplicity problem. How much better does a more complex system need to be? And we're always looking for different ways to develop these types of solutions that are simpler, faster, less computationally expensive. Simpler is always my favorite, right? It's just easier to show that something is transparently superior if it's simpler and does the same job. So that's the big challenge with volt-var.
So do you think we've got there? Can DA solve the volt-var problem given the randomness or the stochastic nature of loads on a distribution feeder?
I think it can make some headway, but the first question we need to ask is, if you are starting to tie all these devices out on the distribution system together and try to increase the efficiency or reliability of that system by coordinating those better, the first question you have to ask is, how much better is it? So as you know, here at SEL, we make a voltage regulator product or a capacitor bank control product. How much better can we make it than if we were to allow those devices to operate on their own with some of the great features they have? So not only that, but in order to make sense of all this data, you have this concept of a model of the power system. You know, who's upline of who and who's connected to which line segment in which phase and what's the impedance of that model. And there's some effort that goes into maintaining that. So you have some complexity there. What is the consequence if we make a mistake in that model? The more complex the distribution system, the more complex the model. So we've seen where volt-var solutions can become slow. Well, how slow is too slow? You'll hear around here often, SEL has this need for speed, right? I really like that as a guy who works with computers all day. How fast can we make it? When you start talking about a computer taking 15 minutes or something to come up with a solution, that's a long time for a computer. That's a complicated solution. So I think we're going to get some benefit, but how much is a great question. So you referenced that loads are transitioning to more constant power type loads. PNNL did a fascinating study where they tried to figure out, if you were to do volt-var nationwide, not volt-var, but specifically voltage reduction, how much energy could we save as a nation? What they came up with was somewhere between, I think, 0.5 to 4%. That sounds like a low number. Is that good? Maybe so. Maybe 4% is worth going for, but it's going to depend on the utility. It's going to depend on the load, and it's going to depend on how simple we as vendors can make those solutions. That's the big challenge for us.
Yeah, about 10 years ago, I had a debate on stage with Jeff Daigle, who's a good friend. Jeff and I went to college together. He's the chief engineer out at PNNL over their volt-var study. And I was very skeptical then of the real true benefits of volt-var optimization at the time. It was really fun. I'll send you a paper of what we talked about, but good times. Yeah, it's really fun. Hey, let's move on and talk about distributed energy resource integration. Certainly, as you pointed out, in the Pacific Northwest, we are blessed with a bunch of hydro. Hydro, to me, is probably the best renewable resource we have. Right? It rains and snows in the winter and the fall. And we store it up in a dam or behind a dam, and then we can dispatch it anytime we want to, as opposed to waiting for the sun to rise or the wind to blow. But the wind does blow here, and it does sunshine. You know, there's a lot of sunshine during the summertime. So we've seen a lot of these resources begin to be integrated into our power system, and with a substantial amount of power now being put into the power system. No longer is it just a handful of kilowatts here or there being put on. These are, when the sun is shining and these solar farms are working, they're putting a lot of power into the system, which means we need to back off on the hydro, right, to match the generation with the load. So how do you see distribution automation being applied for distributed energy resource integration?
So the number one concern often with distributed energy resource integration is their size. The fact that they tend to be, they're not small, like you just said. There's some good size to them, but compare them to Grand Coulee Dam, and we're not comparing apples to apples, right? The big issue with them is they are what are considered to be low energy or low inertia or zero inertia type resources. So we'll back up for a second. A lot of these DERs, these distributed energy resources, are being plugged in at the distribution system. So not at transmission, not next to the dams. They're being plugged in pretty close to where energy is being consumed. In some cases, for industrial customers, they're on site. They're right there. And so there's some interesting automation challenges just right there with coordinating immediately connected load. But power no longer flows just from the substation. And this is not only interesting as an automation engineer or as protection engineers, but this has safety connotations as well. When you trip the breaker at the substation now, is the power off? Can a lineman go work on that? This is the same issue we're having with rooftop solar or anything else. Anywhere there's generation that's sprinkled throughout the distribution system and not necessarily under the direct control of the utility, there are all kinds of interesting technical challenges that pop up. Something that occurred to me that I think is kind of interesting is if you go back to the days of Edison and when we first started doing widely distributed power generation and consumption, it started out as you produce power in one place. So we use the dam, the hydro facility for this example, and you consume it in specific places. You know how power is flowing. But almost immediately we realized, hold on a second, faults can happen on these conductors. I don't want to deal with that up at the dam. I want to deal with that as close to the fault as I can so that I only turn off a little piece of the power grid instead of the whole thing. So we have this concept of reclosers. They're pole top devices and they can trip the line close to where the fault is. So we start adding reclosers and sectionalizers to the feeder. After that, I want to minimize reactive power flow for large customers or all customers. I'm going to put capacitor banks all over the feeder to provide VARs close to where they're needed. So we put protected devices close to where they're needed, VARs close to where they're needed. I want to reduce my peak loading on feeders. So I'll start connecting solar facilities, microgrids, batteries, so that we're reducing peak power close to where it's needed. So as equipment improves, and this goes for protection, automation, or generation, it's allowing us to slowly almost reverse that distance that we've had from generation. So we may soon be running our laundry on a microgrid installed next to the neighborhood pool. Folks who have rooftop solar installations are already kind of experiencing this. So you have this proliferation of not just electronic equipment, but generation as the power system evolves. But back to this inertia thing, solar facilities have no weight to them. They have no spinning heft, right? Like a hydro facility is heavy, and power is observed by a generator as torque. Well, if you twiddle the torque on something that weighs 100 tons or more, it's not going to care as much as something that has no torque at all. And so one of the big concerns is the reliability of the power grid as we start putting these multiple small variable resources on the system. So if you start backing off the dams and all the heavy pieces of generation equipment and using solar instead, what happens if there is a disturbance? How will generation mix react to that? And there are several different concerns that utilities have with the proliferation of renewable energy, or I like to call them variable energy resources. Renewable is good, but that's not really the issue. The issue is that you can't depend on them to be there at all times. When we turn a light on, we expect there to be power. But what if the wind's not blowing? And what if the sun's not shining? How do utilities and independent system operators make sure that there's power there at all times? And that's an interesting problem. There's a lot of automation opportunity in that space.
Yeah, and I that's where I see the biggest opportunity for distribution automation system. Ed calls the power systems with a bunch of distributed energy resources as twitchy. And as you pointed out, dams have a lot of polar moment of inertia, or a lot of energy stored in that spinning mass. The only equivalent you have on a solar panel or solar farm or a wind turbine is the energy that gets stored in the capacitor, right? That's the equivalent of it. So if a fault happens and the system needs to react to be able to supply, say, fault current or keep the voltage up and stuff, is what's ever stored in those capacitors, which is not a lot of energy. So the distribution automation systems have to be a lot faster than they were before to make sure we have a stable and reliable power.
Right.
Okay, so that brings us back to the third item you talked about that falls under this distribution automation control, and that's FLISR, which I like to say that too, which again is the fault location isolation and service restoration. And a lot of that has to do with the fault location, and then once you know where it is, you know how to isolate the affected part of the power system that's got an issue, and then restore service to it. Our first relays have been able to calculate fault locations. The SEL21, the first relay that Ed invented. Ed's father's company built faulted circuit indicators, which allowed linemen to locate where faults were So why do we need this new DA solution for locating faults? Seems like we were doing a pretty good job beforehand with the relays and everything else that we've been creating and selling for the last 35 years.
Right, that's fair. Okay, so when a relay provides an engineer with a fault location, it's using essentially math and physics, and it's observing what's happening on the line. It's analyzing that fault and trying to determine an accurate distance in feet or meters. So the goal is be able to roll a truck close to where that fault is and take care of it. A FLISR solution, again, fault location, isolation, service restoration. We're wasting 3 out of 5 letters there on fault location, or no, 2 out of 5. Anyway, it's looking at it in a different way. So let's walk through real quick how FLISR works. And you summarized it a little bit, but just to give it a little more detail. So you've got breakers, reclosers, and switches sitting out on your distribution circuit, and a fault occurs. Maybe a tractor discs a line, or someone hits a pole, knocks it down, or a tree falls. There's a fault at that point. There's energy being poured into the ground, and the recloser, hopefully the recloser closest to that fault, is going to trip. And if it's a permanent fault, it's going to lock out. Any customers with the misfortune to be downline of that fault is out of power. Their power's out because there's a tree that fell across the line. The goal of a FLISR system is to be able to communicate with every recloser and switch and breaker on that circuit, and every recloser, switch, and breaker on every other circuit adjacent to it, and figure out, is there a way I can isolate that fault better? Can I open a downline switch and then backfeed power from another feeder and restore some of these customers? That is what FLISR's looking for. So FLISR doesn't necessarily care how many meters down the line a fault is. It cares about, is this fault between switch 1 and 2 or between switch 2 and 3, and so on and so forth. Figure out how to isolate it, and then figure out how to route power around that outage area to minimize the customers that are affected. So a FLISR system the goal is to turn a potentially multi-hour outage for a lot of people into a much smaller outage, so that the people we're able to restore experience just seconds of outage instead of hours.
And you, as you described it, you might think it's pretty simple. It's just opening up this switch and closing that switch, but there's a little bit more that goes into it too, right? If you open up one switch and the load required so many watts of power, and you want to close in another one, you got to be worried about, can the line take that extra amount of power that's going to be flowing through it now to service that new load on the line. So it's not quite as simple as just opening and closing switches. There's some calculations and some planning that needs to go ahead before you can reroute power through a particular section of a distribution system.
That's right. And there are all kinds of corner cases there. Maybe there's a hospital on the neighboring feeder, and you need to reserve a certain amount of margin in case that hospital needs to do a high-speed auto transfer onto your source. You can't use up all the margin because there's that high priority load there. Yeah. There are all kinds of issues. They make it a fun problem.
Well, yeah, I bet they do. What kind of switching times are we talking about for a FLISR system? Is it seconds, hours, minutes?
That's a good question. So, and by the way, that's a question that requires, well, I'll answer it this way. When the fault occurs, a protective device is going to trip. And as you started this conversation with, over 80% of those trips are going to end up in a reclose that will leave the line re-energized. So it's really important that a FLISR system let protection do its job. So when we do FLISR, we let that recloser go through its shots. So it will trip and reclose and maybe do a third one, and then eventually lock out. And once that recloser locks out, it may have been 30 to 90 seconds, depending on how that device was set up to operate. Once that's happened, it's just a couple seconds before FLISR has finished its job.
That's really cool. Well, I think I know the answer, but I'm going to ask this question anyway. Why do utilities install FLISR systems?
Right. So this is an easy answer, and it's to increase system reliability and uptime. That's one of the reasons I like FLISR so much, because the benefit is easy to explain and it's easy to demonstrate. So utilities are increasing their number of reclosers. The number of reclosers going out onto the line are getting higher and higher quantity every day. We've got customers now that are telling us, look, if I have 2 miles of conductor, I need reclosers bounding that area. If I have, a couple hundred customers, maybe 400 customers, I need reclosers bounding that area. If I have a certain number of megawatts per zone, I need reclosers bounding that area. They're trying to figure out, how can I sectionalize and react to a problem quickly and with great precision? And so they're adding places where we can automatically break the line with a switch or a recloser all over the place. Well, this can be a problem for human operators. It makes it harder and harder for operators to manually isolate and restore those types of systems because there are so many options. You get this paralysis by analysis going on. So FLISR systems are proven to yield results when they're installed. The yield's easier to quantify too. It's how long was the outage? How long is the average outage when there is no FLISR? Compare the two. So there are reliability outage metrics that utilities track. They track the average duration of an outage, the average frequency of an outage, and they'll track what's called CMI, customer minutes of interruption. They're looking to drive these numbers to zero, no outages, or as close to that as possible. And a FLISR system lets them do that.
That's really cool. And I think our expectation, especially all the time we're spending at home, that our electricity is always available. My CMI should be zero. And I think it was just, as you were talking about that, trying to remember the last time I had an outage at my house. And I, honest to goodness, can't remember when I had one. And that just goes to show how my expectations for reliable electric power are so high. So, Bryan, I'd like to thank you for the conversation today. I would like to have you back at some point, and let's talk about a particular application on how you delighted a customer with a particular distribution automation system. But thank you very much for spending the afternoon with me.
Thank you very much, Dave.
All righty. Talk to you later, Bryan.
Thank you.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.